Hello everyone, this is part 2 of chapter 3, Processes. So as you may recall in the previous section, previous lecture, we went through several aspects of processes. We introduced the concept of a process, we talked about process scheduling, and then we covered operations on processes. In today's session, we will cover inter-process communication, examples of IPC systems, and then finally do a final section on communication in client-server systems. So just to do a quick recap of the previous lecture, we started out with really going through what is a process, and what distinguishes a process from a program. So as we learned, a process is active, whereas a program itself, when it's stored on a disk, is a passive entity, right? So you can have a piece of code that is sitting on your disk, but that is not running, then it is a passive entity. Whereas once you've gone ahead and started execution of a program, and that can of course be done by any number of different ways on modern operating systems. So you double click in a GUI-based operating system, you invoke a command shell and launch a particular program by typing its name, or on a touchscreen system you just double tap on it. All those are acceptable ways of launching an executable. Once you've launched the executable and it is running, it is effectively a process. It is an active executable on the system. One quick consideration here is that a program can manifest as multiple processes. It does not have to, but it can, and that can happen for any number of reasons. One example, of course, could be that you can have multiple users executing the same program. You can also have situations, as we'll see later on, where you have a single program that deliberately sets itself up as multiple processes, right? So you launch the program's executable binary, which in turn spawns a few different additional processes for better performance, as well as potential security benefits. When we look at a process in memory, there are lots of different components herein. The text section is where the actual code resides. The data section is where your global variables are associated with the process. The heap is where you have dynamically allocated memory areas. And then finally, your stack is where temporary data associated with the process, such as function parameters, local variables, as well as return addresses, are stored. They're stored in the stack associated with any given process. When we look at the life cycle of a process, there are several states that a process transitions through as it goes through its life cycle. So when a process is just being created, it is in this new state. As it moves on from being created to being ready to where the process is created, and now it's waiting to be allocated to a processor, that state is known as the ready state. Following the ready state, when you actually get assigned to a processor and actually start executing the instructions within the process, that is known to be in a running state. Your process is in a running state at that point. And then while it's in a running state, we all know modern operating systems are very much interrupt driven. A few different things can manifest. One thing that can happen is that your process actually can get interrupted, wherein it may transition back to a ready state, or the process actually may invoke a scenario where it needs to request input-output, where it transitions at that point to a waiting state, waits for the input-output, and then goes through a cycle. And we'll cover that in just a moment on the state machine. One quick comment here is that only one process can be running on a processor at a given time. Now, of course, as most modern systems have multiple cores, you can have multiple processes running concurrently. So here is really a state diagram illustrating the process transition and life cycle. So we start with the new state where a process again is just about getting created. The process is ready once it is waiting for a processor to be assigned to. Once it has been assigned to a processor, it transitions from the ready to the running state, and now you're executing code in the process. And then one of a few different things can happen. It can get interrupted, where if it's interrupted, it goes back to the ready state and once again waits for a processor to pick it up, or it can enter this I/O event wait status, where it is waiting for input-output, and once input-output comes through, it transitions back to the ready state and gets reassigned to a processor. And then finally, once the code has completed running, as long as there's an exit call, the process gets terminated. Okay, the process control block is really an important element here, which contains all the attributes associated with a given process. So this includes the state of the process, the contents of the CPU registers, the location of the program counter, essentially the location of the next instruction to be executed, and various other attributes. Essentially, the aggregate set of attributes associated with a process are stored in this construct known as a process control block, also known as a task control block. And on Linux, there is a structure called a task struct, which actually stores the process control block, and this can easily be seen within the Linux source code. Furthermore, we also learned in the last lecture that when the CPU switches from one process to another process, the system really has to save the state of the entire state of the old process, and this whole methodology of saving the state and loading the state for a different process so that it can be brought back to the CPU to run is known as context switching. This is a very common occurrence in multi-process systems. It is effectively overhead, but that is the price that we have to pay for having a multitasking system, which can run, of course, lots of different processes, or at least have them scheduled at any given time. We also talked a fair bit about process creation, and then specifically therein we discussed how in Unix, for instance, the whole process of process creation, the workflow therein, involves two steps. It's two system calls. The first system call is a fork system call, which effectively takes a given process and duplicates it, and the second step in the process creation workflow is the exec system call, which typically follows the fork system call in most cases. There are very rare instances where you would just do a fork and let it be and run really a duplicate copy of a process. So you typically do a fork and then you do an exec, and what the exec does is it loads up the new program that you would actually have this process be running. So that is effectively the workflow associated with process creation on Unix systems. And as illustrated in the state diagram, when a fork is executed, you effectively end up with two processes. There's the child process that gets spawned, and then the original parent process, which typically waits for the child to complete through the exit system call. And then finally, the last thing that we covered in the previous lecture was a whole long discussion around multi-process architecture, the benefits therein. So Chrome, the Chrome browser is a good example of a program which actually runs as multiple processes, and the benefit therein, or the benefits therein, are certainly better performance as well as better security. So the renderer process, in fact, there is a unique renderer for each tab that you open up in Google Chrome. And that what that allows Chrome to have in terms of a benefit is if a particular tab or a particular site that you're browsing to becomes unresponsive, or it experiences a security exploit, what really can happen is that just that particular tab can become unresponsive, and that can be shut down without impacting any other tab that is running on the browser. So certainly benefits in terms of performance, as well as likewise with security. If you have a security exploit launched against the browser, what will really only suffer in this kind of a paradigm will be simply that particular process which is running in a sandbox. So the rest of the system is shielded from the impact of the exploit. Okay, so in today's session, we're actually going to focus on the next part of Chapter 3, or the next half of Chapter 3, which is inter-process communication. And let's start off with some quick description of a couple of terms of relating to inter-process communication. So we understand that processes, of course, are active pieces of code that are running on a given system, and they really can be put into two different categories. Processes can be independent, or they can be cooperating. And cooperating processes really can affect or be affected by other processes, including sharing of data. Whereas independent processes are exactly what their name suggests, right? They really cannot be affected by other processes. And generally, in most operating systems, there is clear protection for processes where a given process does not share its memory region with another process, unless, of course, we invoke these special mechanisms for inter-process communication. Now, there are lots of reasons for having cooperating processes. One is you may have a need as an application developer to have two processes which need to share information with each other. You can also have a scenario where you just want to speed up the performance of your particular application by splitting it up into multiple processes, and then having those processes collaborate or communicate or cooperate with each other. Now, of course, this becomes really relevant only if you have multiple processors or cores in the system. If you have a single core system, you're not going to get any computation benefits by taking your program and architecting it so that it gets implemented as multiple processes. If you have a single processor, still only one particular process will run at a given time. You also achieve modularity by virtue of having cooperating processes. And finally, there is definitely convenience associated with that. The ability to have clearly smaller chunks of code, which are more convenient to handle. Now, cooperating processes need some form of inter-process communication. And generally, in the realm of operating systems, there are two well-defined models for inter-process communication. These are known as the shared memory model and then the message passing model. So if we were to look a little bit of a visual representation of these two models, in the first model you have these two distinct processes. So this is the message passing model where you have two distinct processes. They are going to be cooperating, but they leverage a message queue to cooperate with each other, and we'll delve a lot more deeper into that in the next few sections here. In the shared memory model for inter-process communication, what happens is that you have these two cooperating processes that set up a shared region of memory, wherein both of them have access to this shared region of memory. Again, something not available by default for processes, but in this case, both of them agree that they're going to share a region of memory, and therein, what can happen is that one process conceivably can write to that region of memory, read or write, but let's assume for a moment that it writes to that region of memory, whereas the second process reads from that region of memory, and consequently, the two processes are cooperating. Of course, a very common paradigm of this is a client-server paradigm, which again, we will delve into in a few moments. Okay, so once again, when we're looking at cooperating processes, independent processes really cannot affect or be affected by the execution of another process, whereas cooperating processes definitely can affect or be affected by the execution of another process. There are, once again, advantages to process cooperation. These are in the realm of information sharing, computation speed up, modularity, and convenience. Now, if we were just to up-level this conversation just for a couple of minutes here and discuss the pros and cons of shared memory versus message passing as paradigms for inter-process communication. And what we have here is a situation where clearly shared memory is a mechanism that historically has been deemed the faster, and it's clearly been measured to be the faster way for inter-process communication. One of the reasons for this is clearly that the way shared memory works is once you've established a shared memory region to be shared between two cooperating processes, all accesses are treated as routine memory access. There's no need for kernel intervention. There's no need for system calls, right? To set up your shared memory region, yes, you will need a few system calls, but once your shared memory region is set up, there's no overhead. So remember, we were talking about just overhead generally, and definitely in the context of shared memory, that is one clear benefit. There is a significant disadvantage, however, with shared memory, and that comes in the form of cache coherency issues. We will be discussing this a lot more in Chapter 5, but for now, clearly we should take away that when we have a shared memory scenario, and we have a large number of processors and large number of cores with associated caches, the data in those caches needs to be coherent or synchronized, and that requires a fair amount of effort. So that is the disadvantage of shared memory as an inter-process communication. Now, if we were to look at message passing in additional detail, then we recognize that both message passing and shared memory require system calls, but the need for system calls continues to persist in shared memory, in message passing implementations. They're not limited to the initial setup of the shared memory region, as it is, of course, in the shared memory paradigm. The other general rule of thumb has been that shared memory has been a system in an inter-process communication system that works really well when you have larger amounts of data, whereas historically when you had smaller amounts of data to be exchanged, message passing was definitely an easier way to go. Additionally, if you have a distributed system, message passing is definitely a powerful method to implement this versus doing shared memory across a distributed system, a more complex task. And then finally, what's happening is with the evolution of CPU architectures, what's been going on for sure is that we are transitioning to systems which have lots of cores. So 12 core, 16 core, 32 core systems are becoming common, and even a number of cores that are larger than that. And it emerges that message passing is a more effective and a faster IPC mechanism over shared memory as the number of cores that get introduced in a given system continue to scale and trend upwards. Okay, it's just a high-level discussion about the pros and cons of shared memory versus message passing. Okay, so most inter-process communication problems can be modeled as a producer-consumer type scenario. So using that paradigm of a producer-consumer, where a producer produces information and a consumer essentially consumes or drains off that information. If we were to use shared memory to implement this, there can be really two different types of buffers that can be used to implement this. The first is what is termed an unbounded buffer in a shared memory environment, where really you don't put a practical limit on the size of the buffer. And the other method is the bounded buffer method, where there is a well-defined fixed size to the buffer. So if we were to look at some small representation of a shared memory bounded buffer. So here is a paradigm, or here's a layout which is illustrating a shared buffer, which is a circular array with two logical pointers, in and out, where in points to the next free position in the buffer, and out points to the first full position in the buffer. And bear in mind one more time that it's a circular array, so if you can visualize that also, it is definitely a relevant paradigm in a bounded buffer in this particular scenario. So what happens then is the buffer is empty when in is equal to out. And then finally, the buffer is full where in plus 1 mod buffer size is equal to out. And the solution works nicely with buffer size minus 1 elements. Okay, so this is just a representation of a bounded buffer implementation using shared memory. Okay, now with that implementation of the bounded buffer using a circular array, let's see what the code could look like for communication between the producer and the consumer in this shared memory architecture. So here we have sample code where we have a variable of type item, which is termed next produced, which is a variable which will store the next new item to be produced. Right. So again, this is the producer's code structure, and item is the variable that stores the new item to be produced, and then finally. And then we of course transition to this while loop. We're running this all the time, and then further while the buffer is full, do nothing. Right. So we've established the mechanics of what characterizes a full buffer. And if you're a producer and you're producing and the buffer is full, well, you're going to stop producing in this bounded buffer scenario. You say, no more. I'm not going to produce anymore until space clears up in the buffer. And then furthermore, considering that the buffer now, I'm just jumping ahead, but assuming that the little bit of the buffer gets drained, so you're back, you've done your checks, and now there is buffer space that is available. You move on to the next statement here, where you populate the buffer with the next produced item, and then finally you increment the counter for the next, the pointer, sorry, you increment the pointer for the next free position in the buffer. Okay, and the percent buffer size again is mod buffer size because we have a circular circular array. All right, so this is what the producer's code looks like. Now let's look at the consumer. So the consumer's implementation here uses a variable which still of type item, but the variable in this case is next consume, which stores the next item to be consumed. And again, you run the while true loop there, and then while the buffer is empty, do nothing, because I'm the consumer. And I'm of course tapping into the same shared buffer, and I'm saying, hey, is there something there for me to consume? And oh, there's nothing because in is equal to out. So therefore the buffer is empty, and I'm not really going to do anything. And then finally, of course I keep polling, keep checking, and then finally, oh, okay, wait, I have a situation where I have something to be consumed. So I go next consume is equal to buffer out, and then what I do is I increment the full position by 1. Right, the first full position by 1. So out is equal to out plus 1 mod buffer size. Okay. Finally, just a a further overview relating to interprocess communication with shared memory. So we went through various elements of certainly interprocess communication, and then specifically relating to shared memory. Just to recap, so with shared memory, interprocess communication, shared memory is an area of memory shared among the processes that wish to communicate. The communication is under the control of the user's process, not the operating system. Important point to note. And then finally, the major issue with shared memory IPC is to provide a mechanism that will allow user processes to synchronize their actions when they access the shared memory. So what that really means is what will happen when both the consumer and the producer try to access the shared memory concurrently. And synchronization is, of course, the area of concern here, which is discussed extensively in Chapter 5. And that sums up our discussion of shared memory. In the next section hereafter, we will discuss message passing.